lecture in our CLC 642 reinforcement learning course. We're going to discuss now chapter 2 in the textbook, which is discussing multi-arm bandits or stateless MDPs. Again, this is a simplified version of the general MDP that we'll discuss later. However, the solutions that we're going to see in order to optimize a policy for a stateless MDP will help us build a basis toward the more complicated solutions that we'll see later for the general MDP. Okay, so just as a reminder, this is the general course structure, and we're starting, well, from the beginning, discussing stateless decision processes. Okay, so common way in the literature to represent stateless MDP would be the multi-arm bandit problem. So these are slot machines from from casinos, right? And you have a repeated decision to make, which is which one of these machines to play, right? And each one of these machines has a different distribution regarding the reward that it's going to provide you with. So if we were to know the expected, we don't even need to know the full distribution of the reward for each one of these machines. It's sufficient for us to just know the expected reward that we're going to observe from playing each one of these machines in order to decide or to understand what is the optimal action in this case. So we still have our lovely TA with us, Bevha. So what would be the optimal action in this case? So you have actions A, B, C, and D.
Well, it looks like the slot D would give me the highest return, so I'm more likely to play that.
So the highest expected return, right?
Yes.
You don't know. Can you move aside, just show our students the expected reward from playing machine D, and you can really see that machine D has the highest expected reward. So over time, it will be better for you to play machine D or to use action D over and over again. But of course, the more interesting case is when we don't know the expected reward from playing each one of these actions, right? And so we need to learn that while playing, right? While choosing each one of the actions and seeing the results over and over again. So let's say that we don't know the expected outcomes, and now we play each one of these machines, and after playing each one of these machines, we have a pretty good, I don't know if it's a good, but we have an estimation of the expected outcome. And so, by the way, this is an unbiased estimation. If you just take the average of the rewards, if you remember the definition of the expected value, which is just the sum of probability of seeing each outcome multiplied by that outcome. We also have an empirical definition of an expected value, which is just the average of the outcome over an infinite number of tries, times we use that action. But in any case, even if you don't do it an infinite number of times, it is an unbiased estimation. It will converge eventually to the true value, but at any point of time, if you try it less time than infinity, you still have an unbiased estimation, so at expectancy you should get the correct value. So in this case, we played each one of the machines 2 or 3 times, right? And so now we have an estimation of the expected value. So now let me ask you, what would be the best action to choose?
Well, in expectation, I would say slot A.
Right, yeah. So
Yeah.
maybe action A would be seems like the best action to play. And so at this point, you're in a casino, you say, that's it, I converged on my optimal policy, I'm gonna play machine A over and over and over again.
My lucky slot.
Sorry?
My lucky slot.
Yeah, that's it. You're sitting there and let's see what happens. But of course, you sit next to that machine, and over time you continue playing with it, and it will eventually converge on the true expected value, right? And so at some point you're going to see that, well, this is less promising than I expected. And so over time you would like to maybe change your decision, right? Or to learn to converge on the optimal machine while, well, trying all of those. Trying all of these machines in various time steps. We'll discuss this in more details later on. But before we define, we look into the mathematical arguments for how to balance playing the different machines. Let's define some notation just to help us with the math later on. So let's say that k would be the number of actions, the number of arms that we can choose from. By the way, this notation, I try to copy the exact notation from the textbook, just to allow you to later on maybe go over to the textbook, to chapter 2, and read more about these algorithms and these solutions. So I try to keep as much as possible the notation from the book, so this is the notation in the book. T will be the discrete time steps, or the play count, right? So we'll start at time step 0, 1, 2, 3, and at each time step we can play one of the machines. Q star would represent the true value, that is the expected reward of a specific action, action A, B, C, or D. Capital Q, T, would be the estimation, our current estimation, current at time step T, estimation of Q star at time step T. Capital NT would be the number of times action A was selected before time step T, right, for any action. RT is the reward observed at time step T, and A sub T is the action chosen at time step T. Okay, so now we can better define our play process until the current time step, right? So we say that k equals 4, we can choose out of 4 machines. The current time step is 11, that is, we already played. So we played 10 times already, and now our current decision time is time step 11. We have to decide which action to play next. And then we have the observed rewards for each time steps, here, this line. Then the number of times each one of these machines was played. For instance, machine number A was played 3 times. The true expected return from playing each one of these actions is given here. Of course, we assume to not know this, right? This is unknown. And then we have our current estimation based on the rewards for playing each one of the machines. And for this moment, just assume that that we're just taking the average of rewards that we've seen so far. That's our best Q estimation for now. Later on, we might see different approaches, but for now, this will be our estimation. It's also a good estimation because it's an unbiased one. It's easy to prove that, but we won't do it at the moment. Okay, so at this point, after time step 11, we can decide to either choose the greedy action, and a greedy action is a term that we're going to use throughout the course, right? So the greedy action is the action that seems to be best given our current knowledge. So this will be action A, right? Or, so the greedy action would mean that we're exploiting our current knowledge. Or we can choose to explore a non-greedy action in order to obtain new knowledge. So we might, well, if we know the true Q star values, the true expected values, we would say that we probably would like to explore action D. Action D seems to be not very good at the moment. It seems to yield a low reward, but we know if we would have known Q star that this is actually a wrong estimation. If we would continue to play D, we would converge on a better reward.